Welcome to today's paper reading. Today's paper is titled, DeepSeekMath, Pushing the Limits of Mathematical Reasoning in Open Language Models. This paper was published on the AR14 preprint by Zhihong, Shao and colleagues from DeepSeek AI, Tsinghua University, and Peking University. This paper introduces DeepSeekMath 7b, a model that continues pre-training from DeepSeek Coder Base v1.57b using 120 billion math-related tokens. It achieves a notable 51.7% score on the math benchmark, comparable to models like Gemini-Ultra and GPT-4, without relying on external tools. The model's mathematical reasoning capabilities are enhanced by leveraging public web data and through the introduction of Group Relative Policy Optimization, GRPO, which optimizes both reasoning and memory usage. Figure 1 illustrates the top 1 accuracy of various open-source models on the competition-level math benchmark, as reported by Hendricks et al., 2021. This benchmark evaluates the model's mathematical reasoning capabilities without relying on any external toolkits or voting techniques. The figure provides a comparative view of how these models perform in a strictly controlled environment, highlighting their raw mathematical reasoning strengths. Large language models have significantly transformed the field of mathematical reasoning and artificial intelligence. These models have driven advancements in quantitative and geometry reasoning benchmarks, and have been instrumental in helping humans solve complex mathematical problems. However, the most advanced models like GPT-4 and Gemini-Ultra are not publicly available, and the open-source models currently lag behind in performance. In this study, the authors introduced DeepSeekMath, a domain-specific language model that outperforms open-source models in mathematical capabilities and approaches the performance level of GPT-4 on academic benchmarks. To achieve this, they created the DeepSeekMath corpus, a large-scale, high-quality pre-training corpus comprising 120 billion math tokens. This dataset was extracted from the Common Crawl using a fast text-based classifier and further refined through human annotation. The DeepSeekMath corpus is also multilingual, leading to improvements in Chinese mathematical benchmarks. The process of constructing the DeepSeekMath corpus involves several key steps. Initially, the authors use OpenWebMath as a seed corpus to train a fast text model, which is then used to recall more mathematical web pages from Common Crawl. This process is iterative, allowing for the continuous improvement of the corpus. To ensure the quality of the data, the authors implement a decontamination process to filter out any content that matches with existing mathematical benchmarks. This is done through exact matching techniques for both long and short texts. Finally, the quality of the DeepSeekMath corpus is validated through pre-training experiments, where it is compared against other mathematical corpora. The results show that the DeepSeekMath corpus not only covers a larger volume of data but also includes multilingual content, enhancing the model's performance in both English and Chinese mathematical reasoning. Figure 2 illustrates an iterative process for collecting mathematical web pages from Common Crawl. The process begins with a seed corpus, OpenWebMath, which is used to train a fast text model. This model then recalls mathematical web pages from deduplicated Common Crawl data, reducing the dataset to 40B HTML pages. The process is repeated, with additional mathematical web sources identified and annotated to enrich the seed corpus. After 4 iterations, the pipeline results in a corpus of 120B mathematical tokens. Table 1 presents the performance of DeepSeek LLM 1.3b trained on various mathematical corpora, evaluated using few-shot chain-of-thought prompting. The corpus sizes are tokenized with a vocabulary size of 100K. The DeepSeekMath corpus, with 120.2b tokens, outperforms other corpora in English benchmarks like GSM-8K, Math, OCW, SAT, and MLU-STEM, as well as Chinese benchmarks including Kmath, Gaokao Math Close, and Gaokao Math QA. Figure 3 illustrates the benchmark curves of DeepSeek LLM 1.3b when trained on different mathematical corpora. The DeepSeekMath corpus demonstrates superior performance compared to Proof Pile 2 at 50b tokens, indicating a higher average quality. This corpus, which includes data in multiple languages, primarily English and Chinese, shows enhanced mathematical reasoning performance in both languages. Additionally, the DeepSeekMath corpus, being larger than existing corpora, exhibits a steeper learning curve and more lasting improvements in model performance. Table 2 presents a detailed comparison of DeepSeekMath Base 7b against various strong base models on English and Chinese mathematical benchmarks. The evaluation is conducted using chain-of-thought prompting. DeepSeekMath Base 7b demonstrates superior performance across all 8 benchmarks, particularly excelling on the math dataset where it surpasses existing open-source models by over 10% absolute. This performance is even competitive with Minerva 540b, a closed-source model that is 77 times larger and built on Palm with additional mathematical training. Table 3 presents the few-shot evaluation results of base models and solving mathematical problems using tools and conducting informal-to-formal theorem proving in Isabelle. Key highlights include DeepSeekMath Base 7b's superior performance over Lemma 34b, achieving 48.5% on GSM 8K plus Python and 27.1% on Math plus Python. Additionally, it demonstrates capabilities in Mini-F2F benchmarks with 18.9% on Mini-F2F valid and 16.3% on Mini-F2F test. Table 4 evaluates the performance of models on natural language understanding, reasoning, and code benchmarks. DeepSeekMath Base 7b shows significant improvements in performance on MMLU and BBH compared to its predecessor, DeepSeek Coder Base v1.5, highlighting the positive impact of math training on language understanding and reasoning. Additionally, it effectively maintains the performance of DeepSeek Coder Base v1.5 on coding benchmarks, outperforming the general model Mistral 7b on reasoning and coding tasks. In this section, the authors describe the construction of a supervised fine-tuning dataset, which includes 776,000 training examples. These examples cover English and Chinese mathematical problems and are paired with solutions in chain of thought, program of thought, and tool-integrated reasoning formats. The dataset is used to train DeepSeekMath Instruct 7b, which undergoes 500 training steps with a batch size of 256 and a maximum context length of 4,000 tokens. The model's performance is evaluated on both English and Chinese quantitative reasoning benchmarks. Results show that DeepSeekMath Instruct 7b demonstrates strong step-by-step reasoning capabilities, surpassing all open-source models and being competitive with larger proprietary models. In this section, we introduce Group Relative Policy Optimization, GRPO, an efficient and effective reinforcement learning algorithm designed to further enhance the mathematical reasoning ability of large language models, LLMs, after the supervised fine-tuning, SFT, stage. GRPO replaces the traditional proximal policy optimization, PPO, algorithm used in the RL fine-tuning of LLMs. Unlike PPO, which requires a value function to be trained alongside the policy model, GRPO eliminates the need for this additional model by using the average reward of multiple sampled outputs as a baseline. This approach significantly reduces the computational and memory burden during training. GRPO's mechanism aligns well with the comparative nature of reward models, which are typically trained on datasets of comparisons between outputs on the same question. This alignment simplifies the calculation of advantages and stabilizes the training process. Overall, GRPO offers a more resource-efficient and effective method for RL fine-tuning of LLMs. Table 5 presents the performance of various open-source and closed-source models on English and Chinese benchmarks, focusing on both chain-of-thought and tool-integrated reasoning. Notably, DeepSeekMath RL7b achieves significant accuracy improvements, surpassing all open-source models ranging from 7b to 70b in size. Specifically, it attains an accuracy of 88.2% on the GSM 8K benchmark and 51.7% on the Math benchmark, demonstrating its effectiveness even when only trained on chain-of-thought format data from GSM 8K and Math. This performance also positions it competitively against the larger DeepSeek LLMchat 67b model, highlighting the advancements made through reinforcement learning. Figure 4 illustrates the differences between proximal policy optimization, PPO, and group relative policy optimization, GRPO. In PPO, a value function is trained alongside the policy model, which adds computational and memory burdens. GRPO, on the other hand, does not require an additional value function. Instead, it estimates the baseline from the average reward of multiple sampled outputs for the same question, thereby significantly reducing the training resources needed. This approach aligns well with the comparative nature of reward models, which are typically trained on datasets of comparisons between outputs on the same question. In the pre-training phase, code training has been shown to significantly improve mathematical reasoning capabilities, both with and without the use of tools. This improvement is evident across various training settings, including 2-stage and 1-stage training configurations. Additionally, the inclusion of AR14 papers in pre-training data has shown limited effectiveness in enhancing mathematical reasoning, suggesting that further research is required to fully understand their impact. Moving on to reinforcement learning, a unified paradigm has been proposed to analyze different training methods. This paradigm highlights the importance of data sources, reward functions, and algorithms in shaping the training process. Observations from this analysis indicate that online data sampling and robust gradient coefficients can lead to superior model performance. Table 6 investigates the impact of code training on mathematical reasoning using DeepSeek LLM 1.3b. It evaluates performance with and without tool use through few-shot chain of thought and program of thought prompting. The study reveals that code training significantly improves mathematical reasoning, especially in 2-stage training scenarios where 400B code tokens are followed by 150B math tokens. Additionally, 1-stage training with a mix of 400B code and 150B math tokens shows effective mitigation of catastrophic forgetting and synergizes coding and program-aided mathematical reasoning. Table 7 examines the impact of various code and math training configurations on the performance of the DeepSeek LLM 1.3b model in language understanding, reasoning, and coding tasks. The model is assessed on MLU and BDH benchmarks using few-shot chain of thought prompting, and on human eval and MBPP with zero-shot and few-shot evaluations respectively. This analysis provides insights into how different training strategies influence the model's capabilities across these diverse tasks. Table 8 illustrates the impact of math training on various AR14 datasets, evaluated using few-shot chain of thought prompting. The results show that MathPile achieves 16.8% on Mini-F2F valid and 16.4% on Mini-F2F test, while AR14 Red Pajama scores 14.8% on Mini-F2F valid and 11.9% on Mini-F2F test. In contrast, models without math training perform at 20.1% on Mini-F2F valid and 21.7% on Mini-F2F test, indicating that math training does not necessarily improve performance on these datasets. Table 9 examines the impact of math training on various AR14 corpora using the DeepSeek Coder Base v1.57b model. The evaluation focuses on informal to formal proving tasks in Isabelle. The training process involves a 2-stage approach, initially enhancing mathematical reasoning through code training, followed by math training, which boosts overall performance. However, 1-stage training combining code and math tokens compromises mathematical reasoning, possibly due to the model's limited capacity to assimilate both data types simultaneously. Figure 5 illustrates the performance of the DeepSeekMath Instruct 1.3b model, which has been further trained using various methods, on 2 benchmarks. The methods include rejection sampling fine-tuning, RFT, direct preference optimization, DPO, online rejection sampling fine-tuning, online RFT, and PPO/GRPO. The figure shows that online RFT significantly outperforms RFT, demonstrating the superiority of online training. Additionally, GRPO, which adjusts its gradient coefficient based on a reward model, surpasses online RFT, highlighting the efficiency of altering positive and negative gradient coefficients. Furthermore, GRPO plus PS, which uses fine-grained, step-aware gradient coefficients, shows superior performance compared to GRPO plus OS. Table 10 provides a detailed overview of the data sources and gradient coefficients used in various training methods. It categorizes the data sources into online and offline sampling, highlighting the distribution of supervised fine-tuning datasets denoted by The table also outlines the reward functions and gradient coefficients for methods such as supervised fine-tuning, SFT, rejection sampling fine-tuning, RFT, direct preference optimization, DPO, online rejection sampling fine-tuning, online RFT, and PPO/GRPO. The gradient coefficients are specified using equations 10, 14, 18, and 21, which determine the magnitude of the penalty or reinforcement for the data. This table is crucial for understanding the components and mechanisms of different training methods in reinforcement learning. Figure 6 illustrates the performance enhancement of iterative reinforcement learning using the DeepSeekMath Instruct 7B model on two benchmarks, GSM-8K and Math. The data clearly shows that iterative RL significantly boosts the model's accuracy, particularly during the initial iterations. This improvement underscores the effectiveness of iterative learning strategies in refining model performance over successive training cycles. Figure 7 illustrates the performance metrics MASH at K and PASS at K for the SFT and RL versions of DeepSeekMath 7B on the GSM-8K and Math benchmarks, both evaluated at a temperature of 0.7. The data reveals that while reinforcement learning, RL, significantly boosts the MASH at K metric, it does not have a similar effect on PASS at K. This suggests that RL enhances the model's ability to produce correct responses within the top K candidates, rather than fundamentally improving its overall capabilities. DeepSeekMath has demonstrated superior performance compared to all open-source models on the Math benchmark, nearly matching the capabilities of closed models. This model was initialized with DeepSeek Coder v1.57b and underwent extensive training using 500 billion tokens, with a significant portion sourced from Common Crawl's 120 billion math tokens. However, despite its impressive quantitative reasoning scores, DeepSeekMath shows weaker performance in geometry and theorem-proof tasks compared to closed models. For example, it struggles with problems involving triangles and ellipses, suggesting potential biases in data selection during pre-training and fine-tuning. Additionally, its few-shot capability is not as strong as GPT-4's. Moving forward, the authors plan to enhance the data selection pipeline to create a higher quality pre-trained corpus and explore more effective reinforcement learning strategies for large language models. Thank you for watching.